In this video, we're going to look at a question on simple harmonic motion involving derivation of equations. So pause the video now and try all parts of this question. In part A, we're asked to derive this equation. So we know that the trolley is going to experience a force when it's been displaced to one side, and we're told that it has a mass m. So the first thing that should come to mind is that force is mass times acceleration. So therefore, acceleration is force over mass. The second thing we need to think about is what is providing the force. Well, the force is being provided by the spring. So the trolley is displaced to one side, so it's displaced over this side, a distance x, which means that the spring on this side has extended a distance x. So the force due to a spring we know is kx, but that is not the full answer. If it's been displaced a distance x to the right, which direction is the force? Well, the force will be exerted to the left. It will try to pull it to the left, and we signify that direction with a minus sign. So we can then substitute that into here. Acceleration is minus kx over m, and we can say that the negative sign shows the direction of force is in the opposite direction to the displacement. And of course, this is a condition of simple harmonic motion, that acceleration is directly proportional to displacement in the opposite direction. And this will obviously then oscillate backwards and forwards. So we're then asked to show that this expression here can be used to derive this equation here. So we need to use this condition of simple harmonic motion, where acceleration is directly proportional to negative displacement, and we actually know that there is a constant here. We know the constant is angular frequency, where angular frequency is 2 pi f or 2 pi over t, because frequency is just 1 over time period. So angular momentum squared is therefore this squared, which is this squared, which is 4 pi squared over t squared. And what do we notice? Well, actually, we've got the same form of the equation here, haven't we? We've got acceleration is equal to negative k over m x. So what does that actually mean? That means this constant here is the same as negative k over x. If I write it like this, you should be able to see that obviously those two are equal. So we can then say that omega squared is k over m, and we can say that 4 pi squared t squared is k over m, and then if we rearrange for t, we will see that 4 pi squared m over k is t squared, and if we square root it, then we can show that t is equal to 2 pi the square root of m over k. The final part of the question says show that the natural frequency of the mass spring system here is about 0.6 hertz. So the natural frequency is the frequency that it naturally wants to vibrate at when it is moving. Maybe a force has caused it to oscillate. So what we need to do is we need to use our relationship here between the mass, the spring constant, and the time period. We need to substitute in the numbers. So we've been given a spring constant, or a force constant, that's also known as a spring constant, of 4.8 times 10 to the 6 newtons per meter, and we have a mass of 3.5 times 10 to the 5 kilograms. So if we then put that into the calculator, 2 times pi times by the square root of 3.5 times 10 to the 5, 4.8 times 10 to the 6 gives us 1.7. Sorry, not hertz, it's the time period, so this should be 1.7 seconds. Silly mistake. Frequency is 1 over the time period, so the frequency is 1 over 1.7. So 1 divided by 1.7 equals 0.56 hertz, which to one significant figure is 0.6 hertz, which is of course what we are asked